much. Hi everyone. My name is Dominik. As mentioned before, I work as developer evangelist for Twilio. Twilio is basically a cloud communications platform. So we have a bunch of different APIs that allow you to do crazy things like sending and receiving SMS, building video, chat, or voice calls into your applications. But today I'm here to talk about how I hacked my coffee machine, or rather, this was more like the sort of short title that fit into an call for papers. The correct title is how I turned this coffee machine of my flatmate into this slightly tuned coffee machine with the help of my flatmate, a couple of beers, and a Friday evening. So the first thing, typically when I tell people that I have a coffee machine that has an API, they are asking why. Why would you hack your coffee machine? And the main reason for me was that it's interesting. When I was a kid, I used to love taking apart my computer, taking a peek under the hood, trying to understand what's actually going on. My mom wasn't too really excited about this, mainly because she was scared that I'm going to break this and not going to put it all together again, especially once I took apart the computer of my neighbors. But kind of today, we can't do this a lot anymore because the people that manufacture most of the electronics that we use put a lot of effort in us not taking a peek under the hood. So I can't even replace the battery in my laptop or my phone, and I figured let's kind of get back to understanding how stuff actually works. The other thing is I have an Amazon Alexa at home, and I like controlling my stuff, and it's great if you can turn on the lights. But my flatmate was like, it would be great if we could control our coffee. And so far, everything that we had in our apartment was kind of bought with IoT compatibility. And so it was another challenge to figure out how we can actually make this work with IoT, like building our own IoT device and get that integrated into Alexa. And then the other thing is, I said I work for Twilio. We have APIs for everything, and therefore I think everything should have an API. And I figured, why not my coffee machine? And then the other thing is, why would I use JavaScript? Because typically, when you think of hardware hacking, you think of like some low-level C or C++ using an Arduino, and not necessarily using something like JavaScript. And there were multiple reasons. The first thing is I haven't written JavaScript, C++ in ages. Last time I was in university, and I kind of dropped that out of my head. And then, while JavaScript is something I use daily, so I was fairly confident in being able to quickly debug things, kind of prototype things. And so I thought it would be a more suitable thing from that perspective. The other thing is we wanted to have a web server, and since JavaScript is kind of like always bound to the web anyways, writing a web server there is way easier than kind of implementing the same thing in C++. And it's also more challenging because if you try to Google like coffee machine and Arduino, you will probably find one or two results. If you try to find JavaScript and coffee machine, you will find this one. So kind of like playing with no rule book was sort of way more interesting because we couldn't just copy paste code and kind of try that. And then the other thing is I have this theory that hardware and JavaScript are actually like a really nice match because JavaScript is event-driven, and hardware is essentially event-driven as well, right? We want to know when a value changed of a sensor. We want to know when a button has been pressed or similar. And that's something that we do in JavaScript all the time. We have classes that trigger events. We have DOM events. Like we know how to work with events if we know how to use JavaScript. So it's sort of a nice match from that perspective already. And we will see that later, that actually coming into play. And just like anyone who ever wanted to do some hardware hacking, I had a bunch of hardware at home without ever using it. So I had a couple of options actually doing that with JavaScript as well. The first option was Esprino. So Esprino is a project that allows you to run JavaScript on an ESP8266. That's a super tiny microcontroller that you can get that has Wi-Fi built in that you can get for roughly $2 on the internet. And it's extremely tiny. The problem is by itself, you can't just like plug it into USB or something. You would actually need to have something like a Node MCU development board for that to easily flash it. But Esprino also has their own devices, which are these Esprino Pico. that I actually had at home. The problem was that thing doesn't have Wi-Fi, and the solution to get Wi-Fi for that thing is to solder an ESP8266 on top of that, which sounds a bit weird. It is a bit weird, but I also didn't want to bother kind of like soldering this on a Friday evening. It also has a really nice web IDE that allows you to kind of write the JavaScript there. And then the other option was the Tessel. So Tessel is an open source hardware project that currently is the Tessel 2. And the nice thing here is that it has sort of everything that you need for quick prototyping already on the board. So it has Wi-Fi, it has Ethernet, it has real USB ports that you can use to connect something like a webcam or something. It has analog and digital pins, so you can measure pretty much anything you want, and you can set values easily. And the coolest thing, though, is that it runs the full Node.js. So that means we can leverage the existing NPM ecosystem if we want to build something. And that's really cool, because compared to Espruino, for example, we aren't limited to kind of the modules that are being provided, but we can actually like just consume anything that we want. And I'm using that later as well. And then the last alternative was actually Johnny 5. Johnny 5, contrary to the other two projects, isn't actually related to any hardware. Instead, it is actually a Node module that kind of allows you to interact with different pieces of hardware. So initially, this was with Arduinos via the Fermata Fermata protocol. But you can also connect this to all sorts of other hardware microcontrollers, like, for example, the particle photon or similar. And this means that we can, again, sort of use the full power of Node. However, depending on the system that we're running this on, we can't actually execute the Node code on the microcontroller, meaning that if we would try to run this, for example, on an Arduino, we would actually have to connect it to a host system that can run Node, meaning we would have to connect it to a Raspberry Pi, you would have to have it tethered to a computer, or similar things, which wasn't really suitable for this because we didn't want to have something directly connected to the coffee machine, like an additional computer, right? It should sort of be an independent closed-up system. The nice thing is there is a I/O plugin for the Tessel, so that means we can use the Johnny 5 library and all the perks of it, and while running it on the Tessel. And later, if we don't want to use the Tessel anymore, we just need to change a few lines of code, and as a result, we can just port it on any other platform that is supported by Johnny 5. All right, now let's come to the interesting part, and that's how did we actually hack this? And the first disclaimer is neither me or my flatmate are electrical engineers. I gave it a stab in university for 2 semesters and then dropped that, and pretty much with dropping the courses, I dropped my knowledge, which you will see later. So we approached this in a very scientific manner. We took the most valuable tool, most expensive tool that you can have for hardware hacking, a screwdriver, and we opened the machine and just peeked a look at it. It's a bit dark here, but we'll still work. And we found some interesting pieces, and the interesting pieces were sort of in that corner, and there were 3 different pieces. These ones, a microcontroller, a control plate, and an interesting cable. And it's interesting because that was just like an actual plugged-in cable that connected the microcontroller, which is basically the brain of the coffee machine, with the buttons that were kind of our way to interact with it. And that meant that since it's a pluggable cable, we can just take the control plate out and take a look at it. So that's how it looked like. And then our idea was that if we would kind of reverse engineer the protocol that is transferred via this cable, we can sort of spoof the control plate and instead use our Tessel to send in the commands. So in order to kind of reverse engineer the protocol, we just jammed a bunch of jumper wires into that cable. It sort of fits up to today, so sort of works. And then we kind of connected the other side to the Tessel to figure out, connect one side to the control plate and the other side to the Tessel to figure out what's the protocol there. So what did we know just by looking at the board? We knew that there were 8 cables or pins. There were 6 switches, and there were 7 LEDs. So we made some assumptions. At least one cable had to be power. If we look at it, probably going to be the red one. So let's jump back here. Cool. And we needed at least 3 pins plus power to kind of have an idea around the buttons, just based on like a binary protocol. And 3 pins plus power are for the LEDs. And then what's the 8th cable for? Well, we don't know, but we'll figure it out. So again, we kind of started with an actual naive approach, and we wired up the first pin to 3.3 volts because we had 3.3 and 5 volts on the machine. We figured it should work, and then connected all the other pins to the Tesla and set them to analog mode, so that's the 2. And then basically we wrote this small script that would require the Johnny 5 helper library, and it would require the Tesla IO plugin to kind of talk to it. We initialized the board, and then once the board was ready, we created instances for the different pins in analog mode and injected them into the Johnny 5 REPL so that we could read the values. And then we started like just pressing buttons and seeing what happened. We saw that 3 LEDs lit up, but they didn't lit up fully bright. So we figured it might just not be enough voltage. So again, the scientific approach, if you have 3.3 volts and 5 volts, what do? You connect the 5 volts and see if that works. They lit up more bright, and it seemed kind of right. So we're like, all right, should work. I know, very scientific. And then the other thing, the problem, though, was that these analog values were fluctuating a lot. So we couldn't actually figure out if this was because we pressed a button or whether this was just because analog values are fluctuating by nature. So we're like, that's not great, so let's switch this to digital mode. So we just had to switch it back to the default mode. And this sort of helped us because suddenly we were able to both, on the one hand, better kind of manipulate these values by setting stuff on purpose to high voltage or low voltage. And similarly, we were able to read better values, which was just high or low. And based on that, we could figure out that pins 2 to 8 were 2, 3, 7, and 8. Those 4 were actually reacting on button presses in some manner. So the cool thing is that Johnny 5 actually has a class called button that you can just initialize with the pin that you connected it to, and then you can suddenly listen on events like press and release. So this is really where the power of JavaScript comes in, because we don't suddenly have to start looping and figuring out if something changed. We just know, like, either like alert me if it's pressed or alert me when it's released. It's very easy. And based on this approach and kind of randomly setting stuff to high or low, we started taking notes and try different things, and we took more notes, and we thought we knew it. And we were onto something, mainly that we knew that pin 1 was power because, hey, at least 3 LEDs lit up, so we don't know if we broke the others already or not, but 3 lit up, so that's definitely power. Pins 4 to 6 were able to turn these 3 LEDs on or off, depending on whether we set the value to high or low. And pins 7 to 8 would always react on button presses. And then pins 2 and 3 were able to turn off on and off groups of buttons. So if you would set pin 2 to high, you could control these 2 buttons. They would suddenly work. Or if you would set pin 3 to high, you would get these 2 to work. But they would always trigger 7 and 8 when you would press them. So that's not really helpful because, like, if we can only tell you that, hey, 1 of 3 buttons was pressed, how can we tell the coffee machine the other way around, like, hey, press this button? So we had to go back to the drawing board quite literally. At this point, it was, I think, like 4 a.m. in the night. And what we did is we took a picture of the control plate. This was the first time we actually took a picture, and the control plate is only this big, so we were before always like kind of like looking at it. And then we went quite literally to the drawing board by using an open source tool called Fritzing, which is a tool that allows you to draw circuits or schemas of circuits. And so we turned this thing into this thing. And I know it's very cleaned up and it's super useful. But basically what we did is we kind of went along these lines that you can see on the board. And we always measured the resistance between 2 points. And if it was 0, that meant that it was indeed connected, so we didn't screw up the path. And then based on that, we created this diagram. The only thing we dropped was everything that looked like a resistor, because it kind of didn't alter the behavior of what we wanted to achieve. And And that gave us progress because suddenly we realized that 1, 2, and 3 were all power and not just 1. And that explained why the LEDs weren't all lighting up. 4 to 6 were able to control these LEDs, so that makes sense. Basically because LEDs only allow you to let the current flow into one direction. So if you flip it the other way, they kind of go out. And then 7 and 8 were buttons. But that, again, brings us to the same problem. We just get we can just split it up into 2 groups, but we can't actually say which button was pressed. Until we actually took a closer look at the board again, and these 3 things actually have D6, D4, and D3 next to them, and that's because they're diodes. So if you don't know what diodes are just like LEDs, just that they don't emit light, but they still have the characteristic that current can only flow into one direction. And that's useful information because we could redraw our diagram. We dropped all the LEDs because we knew now how we can control all of these. And we just redrew and cleaned up the circuit for the switches using the diodes. And then that allowed us to kind of follow the flow a bit more and understand a bit more what's actually going on. And suddenly all made sense. Basically, it was mappings between the different power pins and the switches. That, however, also meant that making this a digital protocol isn't really convenient because we would kind of need to be on the same kind of rhythm that the coffee machine has. But luckily, my flatmate was smart enough to say before, hey, we should probably look at this thing called relays. And if you don't know what relays are basically a way for you to have a switch that you can digitally control. Like you can turn it on and off, and you can just put wires into it, and then depending on what value you set, you can either open the circuit or close the circuit. So what we did is we sort of wired up the same thing we have here or here, just that we used the relays for it. And we only had 4 relays, so we used 3 of them for the core functionality, which was on-off, espresso, or a normal coffee. And we kind of mimicked the switches with that. So this was our initial setup. This thing, the dark part, is the relays. Because we didn't have enough jumper wires, we had to actually flip it and squash it into the breadboard. By now we have jumper wires, enough jumper wires so that looks a bit more cleaned up. But that was our initial test setup. And then we wrote some demo code, which was basically initializing 3 relays. And then we closed them, we injected them into the REPL, and then we could interact with them in the REPL. So we started off the script at 6 a.m. The sun was already up again, which kind of told us, wrap this thing up. And you can see here, once we run Grande open, in a second, it's too dark. Water is running there. We didn't try it with coffee because we didn't want to risk it and waste coffee. So we were just basically always taking the water and then pouring it back into the machine for test purposes. But yeah, so it was early in the morning. We wrapped this thing up. Basically, we used the fact that this is where the control buttons used to be, and we took them out, right? So there was a hole. So we just put the cable through it, so we didn't have to mash all of that stuff into the casing and put a sticker on top of it. And that's how we called it a day on that night. However, I said I have an IoT coffee machine. This is by no means an IoT coffee machine because you have to connect it to my computer, you have to run the JavaScript code, and then you can use it in the REPL of the JavaScript to control the coffee machine. That wasn't what we wanted to do. And this is where one of my all-time favorite, unfortunately only proposed HTTP status code comes into play, and that's 418 I'm a teapot. How many of you know where this one comes from? All right, a few people. So there is the IETF RFC 2324, which is from 1998, and it's called it proposes the HTC PCP. If you're not good with your abbreviations, that's the Hypertext Coffee Pot Control Protocol, and that was recommended by the IETF as an April Fool's on April 1st. That's why it's still a proposed status code. But I thought I'm going to give you a quick insight in what it actually is about. So it's built on top of HTTP, which is nice because that means I can implement it. It adds a brew method, which acts according to the spec just like the post method. The thing is, they explicitly call out this is not limited to coffee. You could implement a beer brewing protocol and use this brew method. It also alters the safe header option to allow you to define if user is awake to kind of make sure that nobody consumes too much coffee. And it adds the accept additions header, which allows you to ask for things like milk. It suggests the HTTP status code 418 in case you're trying to talk to a teapot instead of a coffee pot. And obviously, we need a new URI scheme, so there's the coffee URI scheme as well. And many other things. It's a great read. This is the accept additions field header definition. Interesting parts about this. First of all, it kind of knew non-dairy milk and stuff like that was definitely on their radar. The other thing is spice type and sweetener type are actually not defined here as what the valid values are. I think this was kind of future-proofing for Starbucks to introduce the pumpkin spice latte. But the more funny thing is this part. So this is the URI scheme for coffee, and it's actually internationalized. So you can see here various languages. I'm German. My attention was immediately caught here. %4b Affe. That's not how we spell cafe. The thing is, in Germany, you spell it with a capital K, and the capital letter had to be escaped. So that's why you use the %4b in order to escape the capital K. So that was how this came to be. Because the others sort of made sense, but like I can write cafe without like using like special characters. The other thing is it has a pod designator, so you can talk to multiple pods with the same protocol if they're under the same host. So obviously, having an IoT coffee machine, I had to implement this, and it's actually working. So this is where we come to the demo part. So because the internet is sort of flaky, I actually need to restart this. So technically, you could run this like independently, and this could just like run forever. But first of all, sometimes if the connection crashes, I have to restart it, and I didn't implement the restart logic yet, so I figured I'm just going to keep it running like this. Oh, sorry. There we go. So I'm deploying the code right now, and in the meantime, I can show you the code. So this is the web server. It pretty much spawns up a normal HTTP server. Once it's spawned up the server, I use a tool called local tunnel to actually have a like externally available URL that we can use. And then it initializes the coffee machine, and then once it's ready, like it just prints that. Obviously, I check for if it's a teapot just in case like I mess something up. And a bunch of other things like here, I'm checking for the brew protocol, all the important things. I actually had to alter the URI scheme a bit, which I'm going to show in a second. I checked for authorization because I don't want you to control my coffee. I checked for the correct headers. I had to add another one, and that's for using Alexa. I checked for the accept additions, yeah. So basically, the reason why I had to alter the scheme was that I'm using an Alexa skill here via IFT, and IFT doesn't provide, for whatever reason, application coffee pot command as a valid content type here. So I was a bit upset there. All right, I heard it clicking here, so that means the thing is on. Let's see. So this was just a normal GET request to pod 0 to see if the coffee machine is on or not. And it is, so we can go and code. So I said I altered the URI scheme a bit. And the basic thing that I added is a sub-resource called espresso because I don't have multiple pots, but I have different flavors or like different types of coffee. And I added this authentication token. So all we need to do here is we just need to quickly do an HTTP post request because GOT doesn't have a brew method. Again, not really future-proof. And then we just need to set the correct headers here, obviously. So that's content type, application, coffee pot, command. And there are only 2 valid values for this. One is start, which is the one that we're interested in. And I'm just going to console log. Enjoy your, put an emoji in there. Cool. So that's all I need, hopefully. So let's run this. And if everything worked well, let's see. Come on. Come on. No! Process out of memory. That's very ironic. All right. So we still got 3 minutes, so we still got the time. So I'm going to show you, in the meantime, how the actual, because so far I only showed you the web server, the actual way I'm interacting is just like the demo script that I showed earlier. So I'm actually just creating here some relays once they're ready. And then in order to press the buttons, I have a press button function here. And all that does is it opens the relay. And then after 500 milliseconds, it closes the relay. And the reason for that is that the coffee machine has this custom behavior that if you keep the button pressed for longer than a very short time, and then release it, it will actually just make coffee while you keep it pressed. While if you just press it shortly, it will do the right amount of water and coffee that you actually requested for that type. So that's how I did that part. The other thing is you might see, if you're sitting close, these LEDs. So right now the is on kind of thing is very faked because it's sort of harder to measure these values, so we didn't have the right tools to do that when we initially hacked this. All right, so this clicked again. The coffee machine is running. Come on, don't run out of memory. Yeah, there we go. Finally, coffee worked. All right, so let me jump back to my slides. All right, so this is what we have got so far. We didn't have time recently to work further on this. You can find the code on my GitHub, including the script that triggers it and things like that, and schematics of the wire up and things like that, so if you want to check that out. Let's talk about what I learned doing this. Obviously, I should have learned something when I'm wasting my time with things. So first of all, reverse engineering is fun. Actually being able to take a look at stuff and trying to figure out how it works. It's just so much fun. And most companies work nowadays hard to not allow you to do it. But if you have something, especially that you can spare, we had 2 coffee machines, no worries. There was no risk involved here. Then peeking under the hood is a lot of fun. So if you know that your something broke, for example, just take a look under the hood. Maybe you can even fix it. Reverse engineering is very frustrating. We broke at least 1 or 2 LEDs on the actual control plate. And the problem is, contrary to software development, if you break something, there's no git revert. Meaning on a Saturday morning, you can't just be like, it's 5 a.m., I'm just going to get a new resistor because you burned through them all. So replacing stuff at 5 a.m. is hard, or generally, you can't just download something new from the internet. So always keep that in mind and have some backup stuff when you're trying to hack something. JavaScript and hardware work incredibly well together, especially if you're a beginner, because it just enables you to kind of understand things way nicer and write understandable event-driven code. Tesla 2 is great. It's a great project that you should totally support. It's a great way to get started with hardware and JavaScript, just because you can just run the code there, you can push it there. They have great documentation on it, and all the folks are just working on this in their free time, so there's no company behind this. Johnny 5 is super useful. It's a kick-ass module that allows you to easily get into hardware because it has a class for pretty much anything that you need as a hardware component, so that's super useful. And it allows you to write portable code, so if we decide we want to use something else, the Tesla for something else, we can just swap that out for some other piece of hardware and keep the hack running. So what's next? I need to figure out a way to programmatically determine the state. That's mainly due to down to me buying the right components to measure the voltage of a different circuit. And then add more relays so we can use finally all 6 buttons of the machine. And then I'm always up for suggestions. So I heard of like people suggesting I should have an RFID scanner to figure out if there is like a coffee mug underneath it. We still have to figure out how to swap these capsules that it uses. So I'm open for creative suggestions there. If you want to read up this whole thing again, I published on April 1st this year suitably a blog post about the whole hack. And you can check it out on this URL. I'm going to tweet about it in a second as well. And then I put up the slides on Speaker Deck, so you can follow this URL. Again, I'm going to tweet about that. And with that, I'm pretty much on time, so I would like to thank you all. And if you have any questions, I'll be around for the rest of the day.